एक्स्ट्रा क्लासेस लगेंगी।
चेक करते हैं।
जहां उनकी नजर हो, आप
He was an aerospace research center research associate for many years, and then he was a graduate research fellow at Columbia University, and he was a visiting professor at the Indian Institute of Science, Bangalore, at the Divecha Center for Climate Change, and he is a visiting professor at IIT Pune, IITM Pune, since many years, 2011, and Dr. Raghu is credited with many books and book chapters, about 10 of them, and he had more than 150 peer-reviewed publications, and then he has given more than 186. Voice okay. Yeah. Yeah. He has given more than 186 seminars and invited talks. He has many honors and awards to his credit, more than 25 of them. And then with this little introduction of Dr. Raghu Murtugudde, I now welcome him to give his talk on the ocean's role in monsoons. Yeah. Dr. Raghu, you can start now.
Okay, so everybody can hear me, I hope. If not, you have to send me a signal somehow.
Yeah, so we are able to hear you. Yeah.
Okay, so I'm going to do it as a lecture, not as a seminar. So I'll just raise many questions along the way, since this is supposed to be for students. I'm going to touch on monsoon variability and trend and extremes, but try to bring up what the ocean's role could be, because not many things are known. Indian Ocean is always there. It's warm, but we don't seem to know very well exactly what role it plays. There are many hints for it. There are many papers, but in terms of actually using that to improve coupled models of forecasts, that's not been so easy. So if you start with this distribution of rainfall for the summer monsoon of 2020. So this goes from 1st of June to 30th of September. I think the withdrawal actually happened a little bit late, but officially we just say that's the season. And you can see that in the beginning there was a couple of cyclones, I think Amphan and other one I forgot. They were able to pull the monsoon trough and make the monsoon happen on time, even though the north-south temperature gradient was not favorable for an onset arrival. After that, there were several depressions and so on, which produced this strange distribution. So where it is green, it is normal. Where it is bluish, it is
Hear us? Yeah. We are not able to hear you, Raghu. Yeah.
Because I'm hearing your introduction, there is somehow a tape playing.
Okay. Yeah, now we are able to hear you. Yeah. Can you continue? Yeah. There is a disturbance, but here nothing is happening anyway. Yeah.
Yeah, some video is playing in the background for me. I think I stopped it. Can you hear me now?
Yeah. Yes. Yes.
Can you see the screen?
Yes. Yes.
Okay. Somehow the YouTube video started playing, so maybe they are playing and it's playing on my screen. Okay, so this distribution is very odd. You can see there are normal and normal rainfalls with this strange pattern of below normal rainfall from Jammu Kashmir down into the country towards Delhi and here in the far northeast corner. So obviously all this moisture has to come from the ocean, except for whatever gets recycled over the Gangetic Plain. So what is the role of the ocean in determining such a strange distribution? What is the combination of land processes, atmospheric processes, and ocean processes that determine the distribution? This is not, we are not even very close to describing the processes in the distribution. But when we look at the all India average, we get some behavior that seems to be that the seasonal mean remains within plus minus 10%. And I would suggest, if students are interested to explore that, if you look at the summer months here, you can see that the ITCG splits. The marine ITCG still remains here because the ocean is warm, as we will see in a minute. And then you get rainfall over Western Ghats, Himalayas, and the core monsoon zone, and over the Bay of Bengal. So here, coming up in summer months, you have basically double ITCZ. So if you think about the African highlands, the Burmese mountains, and the Himalayan mountains to the north, and the warm ocean, as the sun crosses to the north, maybe there is some kind of an energy that gets set up over the Indian Ocean and Indian subcontinent that determines how much rain has to happen. So maybe the ocean rain plus land rain together is determined by the energy, so that doesn't vary more than plus minus 10%. But that doesn't help farmers because the distribution of rainfall is what matters to them, and the distribution within the season in terms of active and break spells. So this, I took global picture here basically because you can see the ITCZ, SPCZ, and the Atlantic, South Atlantic convergence zone and so on, which gives you a sense that monsoon is probably part of the global circulation, global dynamics. We always zoom into the Indian Ocean, zoom into the Indian region, and we keep worrying about the monsoon, even though the westward moving intra-seasonal oscillations come from the West Pacific, and there is the El Niño impact, and there is the Atlantic Ocean impact, but a lot of the focus tends to be on the Indian Ocean itself. If you look also at the sea surface temperatures, as the sun moves north, the warm pool in the West Pacific moves, and the Indian region also gets warmer to the north over the Bay of Bengal. But the Arabian Sea has this strong upwelling by the southwesterly winds off of Somalia, which breaks the ITCZ, in fact. So you have warm enough ocean that it can still maintain an ITCZ throughout the summer, even though everywhere else ITCZ moves north with the sun. So if you look here, the cold temperatures here actually almost break the ITCZ by the upwelling and the cold temperatures, which cannot support the convection. So you can clearly see here that the rainfall almost disappears. So the East African regions get rainfall during the inter-monsoons, during the March, April, May, and October, November seasons. So those kind of processes are not very well understood because we keep looking at these kind of ideas that Indian Ocean is warm and it looks like it is related to the rainfall. But if you look at the summer temperatures here, I will show a little bit later on that the high rainfall over the Western Ghats and over the Bay of Bengal close to the Burmese mountains are controlled by very different processes. And you can clearly see here the marine ITCZ or the ocean ITCZ. And of course, up there is Himalayan foothill heavy rainfall with core monsoon zone getting some rainfall as well. So this rainfall over the Indian region is often referred to as the tropical convergence zone by Sulochana Gadgil and so on. But when you look at this, it doesn't really look like an ITCZ. This looks like an ITCZ. This looks like an ITCZ. There's ITCZ there, but there is some sort of a mess here. So why do we call that an ITCZ? So the ocean seems to do a lot of things there that we haven't understood very well. The other point I will raise is that if you look at the time scales of things, I'm just showing here that's warm temperatures over the Indonesian seas during the northeast monsoon and the southwest monsoon. So the time scales of inherent intrinsic variability on the eastern side are in the quasi-biennial time scale. So it is dominated by El Niño time scale, even though southern oscillation and the El Niño sometimes have quasi-biennial time scale. But sorry, this one is the eastern side, Indonesian temperature and to the east. But if you come towards the Indian Ocean side, then you actually get a very dominant biannual time scale. So we don't know exactly what changes the time scale, but the two are related through this central pole. Some people call this the Indo-Pacific tripole. So you have El Niño on the eastern Pacific side, you have the western Indian Ocean, and in the middle you have the Indonesian seas, West Pacific warm pool, and the eastern Indian Ocean, which are all warm temperatures, as we can see here. So if you look at the correlation of the Indonesian rainfall with rainfall everywhere, you can see that in March, April, May, there is high correlation over here. During June, July, August, the correlation is high here, and associated with that, you have these along-shore winds, which actually create the upwelling, which looks like an IOD, Indian Ocean dipole-like circulation. Also in September, October, November. So the correlation of March, April, May rainfall over the Indonesian seas is correlated with sea surface temperatures into the September, October, November season. And you can see this is a clearly IOD signal. So then the question rises whether IOD is really something that is closely related to the variability over the Western Pacific and the Indonesian seas. The trigger mechanisms of the IOD are not very well known. The time scale doesn't seem to exist. It's very episodic, what happens once in a while. But when it happens and when it's strong, then there is the so-called weirdness feedback here, where you have thermocline moving, sea surface temperature cooling, maybe east-west SST gradient, creating these winds which have a positive feedback, which is very obvious in the Pacific Ocean during El Niño, and also obvious during the Atlantic zonal mode in the Atlantic Ocean. So Indian Ocean also seems to have that. The other additional thing here is that the convection is always triggered in the Western Indian Ocean, especially Southwestern Indian Ocean, throughout the year. During the October to April season, the MJOs propagate eastward. They go across, they go across Indonesian seas, and or sometimes they get stuck here, or sometimes they get detoured south. But during April, May, when the ITCZ wants to move north, then those convections begin to propagate northward, which we call the monsoon intra-seasonal oscillation. Okay, so during El Niño years, for example, MJOs remain strong, and sometimes monsoon has a drought. So what is the relation between these eastward propagating systems and northward propagating systems, and the fact that they have a season that is split into two, October to April and May to September? And what is the role of the ocean in that? What is specifically, what is the role of the Western Indian Ocean in triggering these convections? What is the role of the Eastern Indian Ocean in terms of the ITCZ split and the maybe detouring the MJOs northward in the boreal summer and southward in the boreal winter? So those intra-seasonal timescales are also important, because if you look at the monsoon, we always worry about seasonal monsoon because it has got a strong seasonality. But within the season, the rainfall is distributed as active and break spells. So these are shown for 3 years. The envelope here is the climatological daily rainfall. July, August is the season with the top rainfall. June is the onset and September is the withdrawal. If you look at 3 years, 1972, which was a strong El Niño, 2002, which was a El Nino, but it is the so-called Central Pacific El Nino, where the warming is near the date line. Both were drought years. 1994 was a mild El Nino year, but it also had a very strong Indian Ocean dipole or the zonal mode. And the monsoon was not a drought that year. So at least visually, you can see that these red colors, which are below the envelope of the climatology, are the break periods when the rainfall is happening over the ocean and not over the land. And the blue colors, which are above, is when the rainfall is happening over the core monsoon zone. So you can see that during the drought years of 1972 and 2002, there appear to be more break periods and longer break periods. Whereas in 1994, which is a normal year or slightly above normal year, there are more active years and very few break years, break periods, active periods and break periods. So what is the relation between external forcing like El Nino and the Atlantic El Nino or the Indian Ocean dipole and the active break spells? We don't know, because to the extent that there is an intrinsic time scale that gets selected in terms of intra-seasonal variability of MJOs and mesos, and to the extent that the active and break periods of the monsoon are related to meso, we don't know the role of the large-scale dynamics and the oceans versus what is happening on land. This looks complicated, but I will just make a couple of points. As we said, we always look at the sea surface temperatures and say that rainfall is related to warm sea surface temperatures. But actually, over the ocean, yes, that is true. Bay of Bengal is typically much warmer during the summer monsoon season, and there is a lot of rain there. In the western part over the Arabian Sea, there is upwelling and cooling here. Can you see the cursor that I keep moving? Hello?
Yes, Raghu.
Okay. So the Western Ghats rain here, if you do the calculations, the potential energy to kinetic energy transfer calculations at intra-seasonal time scale, and look at what controls the moist static energy, the moist static energy expression is given here. I won't go into the details, but you can read up the papers. I can send the references. It turns out that over the west coast of India, the rainfall and so here is the sea surface temperature and the rainfall, and the rainfall is here in black contours, and the OLR is shown here in the colors and white contours. I think, I hope so anyway. But the main point is on the western coast, the warming of the ocean happens first and then rainfall happens, because it seems the moist static energy is controlled by the ocean. Whereas over the Bay of Bengal, you can see that the rainfall and the sea surface temperatures are not so, and the moist static energy are not so closely related. So the colors here are moist static energy, sorry. So moist static energy buildup happens in the western coast before the rainfall, and the warm SSTs happen before that, but there is no such relation in the Bay of Bengal. So it seems that the Bay of Bengal, as long as the SSTs are above the threshold of 28 degrees centigrade or so, it is the atmospheric instabilities, the conversion of the potential energy to kinetic energy, which is typically associated with the convective events and convective heating and vertical motion. That is what determines the rain, whereas on the west coast, the ocean controls. So you can think that the southwesterly winds are coming here and they slow down to go up the Western Ghats. As they slow down, the latent heat loss is reduced over the ocean warms, and then ocean begins to control the moist static energy instability and creates this rainfall, which we always think of orographic rainfall, but actually if you look carefully, the rainfall maximum is away from the Western Ghats and over the ocean. So ocean has a strong role to play there. Okay. Then the other question is for active break periods over the land, where does all the moisture come from? So this is again a little bit of a complicated calculation, but I will just explain in a simple way so you can just follow the logic of the processes. This is done with something called dynamic recycling model, where it's like a back trajectory model, but you figure out where the moisture is coming from by using back trajectories, but along the way you have sources and sinks like evaporation and precipitation. So if you look at active period over the Ganga basin here, the source of moisture is coming from the ocean, and this place is dry. Okay, this also means that the Ganga basin itself is contributing to rainfall over the Ganga basin, which means there is a lot of re-evaporation and recycling happening over the Ganga basin. Okay, so if you assume that there is an average of let's say 800 millimeters of rain in a season, during the active period, active and break periods, there is recycling of the rain that is falling, that's happening. But if you look at the break period over the Ganga basin is losing water and it is supplying water to the northeast. So there is this east-west pattern which is related to recycling over the Ganga basin. So Ganga basin is not only recycling and producing more rain over itself, but when there is a break period, the evaporation over the Ganga basin is actually supplying the rainfall over northeast region. So essentially you have this north-south pattern which is related to ocean supply with the south westerly winds and the turning around winds caused by the southeasterlies coming over to land from the Bay of Bengal. So you can actually calculate how much moisture is coming from here, from the south of the equator and from the Bay of Bengal and so on. And that raises a question of what happens to these sources and sinks when the ocean begins to warm. Because the land source is very limited. There is not much water on land, right? Even the recycling over the Ganga basin is related to soil moisture and whatever irrigation happens over that region, because this is the breadbasket of India. There is a lot of agriculture, a lot of irrigation. Even in a good monsoon year, there is a lot of irrigation. That irrigation water is getting recycled. So the deep question there is whether irrigation increases the monsoon or decreases the monsoon and so on and so forth. But the main point would be to see what the ocean's role is in supplying moisture onto land. Especially because when we talk about the extremes, we will see that the heating over land doesn't correspond to the extremes over land. So moisture has to come from the ocean when there is a demand for moisture on land. So land is not the major water source. Okay. The other way to look at the role of the ocean is to think about the El Niño and droughts and floods. So this is the long-term rainfall anomalies over the Indian subcontinent, so-called all India monsoon rainfall. And obviously the blue lines above the zero line are wet years and the red lines below are the dry years. And the stars here correspond to La Niña and El Niño. As you probably all know already, only about 50% of the drought years correspond to El Niño years, and about 50% of the wet years correspond to La Niña years. So even though we think El Niño causes drought, actually only 50% of the droughts are explained by El Niño, and we'll see that Atlantic Ocean has a big impact as well. But monsoon obviously can generate its own droughts by what we would call internal variability. Then the question is, what is the role of the monsoon in the El Niño and Indian Ocean dipole and so on? So the SST patterns associated with the so-called Indian or Indo-Pacific tripole, with the positive here, negative in the middle, and positive on the west, or you can see that this is an El Niño pattern where there is warm SSTs here, which obviously changes a little bit based on whether it's a Central Pacific El Niño or it's an extreme El Niño or it's a canonical El Niño and so on. You can look up those, the terminology in these papers like Dakchen's paper from 2010 and 2015 and so on. So we have talked about the relation between the Indonesian rainfall and sea surface temperatures here and potentially the IOD. And we have talked about the MJOs and MESOs. And we are saying only 50% of the droughts are explained by El Nino. So the other 50% have to be understood in terms of what these oceans are doing here and whether that relates to the change of time scale going from quasi-quadrennial time scale on this side to the quasi-biennial time scale on this side. There are many ideas on where the quasi-biennial variability comes from, which has to do with the persistence of the SST anomalies and the change in the winds because of monsoonal circulation and so on. But it's not used very well so far to improve either El Nino prediction or the monsoon prediction. So you always have to think of these things as whether they advance the understanding enough to improve predictions. That's one of the goals anyway, but for a country like India, that should be kind of the main goal. How can we improve monsoon predictions, especially the distribution of the monsoon? Many of you probably know that the Atlantic Ocean also has what is called an Atlantic Niño. So you can think that the convection here, which is the biggest center of convection, moves around at various time scales, intra-seasonal to intra-annual and maybe even decadal time scale. In fact, it does do that in decadal time scales as well. Whenever there is a perturbation of convections, you have wind anomalies, rainfall anomalies, and waves, Rossby waves, Kelvin waves, and so on, which can directly affect the East Pacific and create El Nino. But they indirectly affect the Indian Ocean on this side and the Atlantic Ocean on the other side. Because the Atlantic Ocean and the Indian Ocean are much smaller than the Pacific Ocean, the El Nino-like mode in these oceans are very short-lived. This only happens in September, October, November, and this only happens in June, July, August. So the Kelvin waves and Rossby waves here will move across within 10 days to the east and 1 month to the west and so on. Nonetheless, there are processes that are common, like the Bjerknes feedback that I mentioned, where the wind anomalies generate upwelling anomalies, thermocline anomalies, which affect the SST, and that affects the SST gradient. The SST gradient affect the winds. Winds again affect the upwelling and SSTs, so you have a positive feedback. Okay, so this work basically argued that if you look at the difference in the monsoon for a cold Atlantic zonal mode and a warm Atlantic zonal mode, then actually there is a tremendously strong signal. There is a very strong signal along the Western Ghats, and there is a very strong signal over the core monsoon zone. And these papers, there is one more that I haven't listed here, show that the waves set off from here because of the convection anomalies affect the depressions that form in the Bay of Bengal and bring rain over here, contributing 50–60% of the rain, which are also related to monsoon intraseasonal oscillations or the northward propagating features. So the Atlantic zonal mode is also affecting the Indian monsoon. So then the question, of course, is whether that happens during the same years as El Ninos or during non-El Nino years. If there is a strong signal from the Atlantic Ocean during non-El Nino years, then maybe that can improve your predictions. And it turns out that, in fact, these are independent and many times happen after an El Nino or before an El Nino or during a La Nina. So there is prediction that can come from the Atlantic Ocean for the monsoon that is independent of El Nino. Of course, if you remember the ITCZ, then the ITCZ goes across the Atlantic, the Indian and the Pacific Oceans. So if you are looking for a PhD thesis, you would probably think maybe there is a connection between all of them. Okay, so let's move towards, I don't know how much time I have, but I'll try to finish up in about 10 minutes. If you think about the warming, this is the annual warming trend from, I think, 1901 to 2017 or so. And we know that the Indian Ocean is warming quite rapidly, other than this warming hole here, which is potentially related to the Atlantic meridional overturning circulation. Everywhere it's warming, but Indian Ocean is warming quite rapidly. And to again mention the role of the ocean, of course, the question is when Indian Ocean warms, then what happens to the moisture supply to the monsoon, as well as what happens to the north-south temperature gradient, land-ocean temperature gradient. Indian Ocean receives some heat here through the Indonesian through flow. And there is some evidence that with global warming, the trade winds are getting stronger and more heat from the Pacific is coming into the Indian Ocean. And there are now new papers just coming out showing that the Southern Ocean is warming. The Southern Ocean is very special because it's a channel, so the warming penetrates very deep because the wind forcing and the Ekman currents go very deep in the Southern Ocean because there is no boundary here. If the winds try to too much energy blowing from this way or this way, then the boundaries prevent more energy going in. So only 2 to 5% of the energy goes into the ocean, whereas here in the Southern Ocean, much more energy can go in. And that water is coming into the Indian Ocean as a part of the Indian meridional overturning circulation. So water is coming in and the deep and intermediate ocean and has to upwell and go back south, because there is no way to go north here, unlike in these oceans. So there is a heat balance that is related to the Indonesian through flow as well as the Southern Ocean connection. And there is a strong seasonality. Typically, we always look at the summer SST trends. This is from Roxy's paper, which argues that the maximum warming is happening here in the Western Arabian, Central Western Arabian Sea during this period, during the summer months. So how do we relate that to the trend of the monsoon? So I'll come to the trend of the monsoon, but first I will mention this. The monsoon is basically defined by the onset, which is shown here, the withdrawal in the middle of September, which is shown here, and the length of the rainy season. Basically, the onset and the withdrawal together determine how long the rainy season is. And then the question is how the rainfall is distributed in the season in terms of active break periods, number of rainy days, and so on. And these are the mesos northward propagating. You can see they are going from 10 south to 25 north. And this is the lead lag responding to. Is there some sound that I hear? Everybody can still hear me?
Yeah, we are able to hear you. It's clear, Raghu.
Okay. So this is showing that basically the onset used to happen few days before June 1st, before the 1976 regime shift of climate, which is well known. And after that shift, the onset has been delayed by a few days. So systematically, the onset is arriving later. There is no strong correlation between the onset and the seasonal rainfall, but in general, it turns out that if the onset is late, then generally it doesn't turn out to be a wet year in general, okay? And in this paper, the argument was that the withdrawal, which used to happen around the third week of September before 1976 climate regime shift, is happening a little bit earlier, by almost a week earlier, which means the seasonal length of the season is compressed. Of course, in the last couple of years, the monsoon is not ending at all. It is almost continuing into October and merging almost with the northeast monsoon. So this study has to be looked at again. Nonetheless, if the season is compressed because the onset is later and withdrawal is earlier, then is that going to lead more extreme rainfall? It depends on whether you are going to put the same amount of rain in a shorter season. Okay, so then that depends on the seasonal trend in the seasonal rainfall, which I'll show in a minute. I'll also add that if you look at the northward propagating speed before the regime shift and after the regime shift, sorry, the dashed line is before the regime shift, it used to move faster northward, but since 1976, it seems to be moving slower, which generally is consistent with the slowdown of the cyclonic systems in a warmer ocean. So again, there the role of the ocean is not very clear, but in general, it turns out that if we go back to the intrinsic time scale, which is the active break period time scale, the warming period has more intense active periods. So extreme rainfall is happening in the active periods. The break periods are more frequent and longer. So the distribution of the active break periods is also changing, which means the length of the rainy season is associated with compressing the rain into shorter active periods and creating extreme rainfall. I hope you are following the logic. Just think through it. I hope this is being taped so you can listen to it again. If you compress the seasonal cycle and increase the number of break periods, then you will have to increase the rainfall in the active periods unless the rainfall decreases a lot. Okay, this is just saying that the spatial variation of the mean rainfall is decreasing, but spatial variations of heavy rainfall is increasing. So there are many things happening. Everything about the monsoon seems to change, but I would suggest that you focus on the intrinsic timescales like the active break periods and see how they are changing and whether that can explain almost everything. Okay, so here is another relation to the ocean that we can try to understand. That is the correlation between rainfall and SST in two products. And you can see that there is this horseshoe pattern where rainfall has decreased, which you can see here. And that is associated with the warming over the ocean. Of course, the correlation is high because the correlation between trends is very high, always high. But it's also not clear whether the precipitation is really decreasing or there is a regime shift that happened somewhere here in the 60s and 70s, or whether there is some sort of a cycle of 20, 30 years in the monsoon and monsoon is returning to normal again. So question is whether monsoon normal means seasonal amount of rain is normal, like 900 millimeters per year, or does it mean that there will be not extreme events? So that is a more difficult question. It is possible that we will have the same amount of seasonal rainfall, but extreme events will still increase. So in that case, the definition of normal has to be thought of carefully. So just to give some flavor of your neighborhood, Andhra Pradesh, you can see that the seasonal rainfall, the monthly rainfalls show kind of trends that seem to be significant, but it's not very well understood why the June rainfall could be increasing while July and August could be decreasing, and then September increasing again, and so on and so forth. In general, if you look at the seasonal or the annual rainfall, both, so here is the annual rainfall, which seems to be decreasing. I don't know how much northeast monsoon Andhra gets, obviously significant because the trend of the southwest monsoon rainfall is either flat or maybe slightly increasing. Okay, so you have to understand not only the southwest monsoon, but also the northeast monsoon and see what determines the spatial heterogeneity and so on. The other detail is that the spatial extent of the extreme rainfall seems to be increasing as well. So that is the trend we saw before. And this is the extreme events in terms of rainfall greater than 150 millimeter per day. They used to be about 2 per year. Now they seem to be happening about 6 per year. So there is a threefold increase in widespread extremes. And the scale is now almost 10,000 square kilometers. So it's not only that extreme rainfall is increasing, but they are becoming more widespread. There is very nice papers by people from IISc like Akshaya Nikumb, who is Arindam Chakravarti's student. These are papers from Roxy that you probably know. Akshaya's paper talks about how processes originating in the east and west combine together to produce these large-scale rainfall extremes. So those are also interesting things. Again, they relate to the ocean. But nonetheless, it turns out that when there are extreme rainfalls here, a lot of the moisture actually comes from the Arabian Sea, which is warming quite rapidly as well. So that's something to remember. So this is just the moisture supply again here, showing that during extreme events, Arabian Sea is contributing almost 36%, losses coming from here. Bay of Bengal contributes only 26%, and Central Indian recycling is contributing 29%, and the Central Indian Ocean is contributing only 9%. So then we have to watch for the warming of the Arabian Sea. Plus, it also means that even if we do everything to adapt and mitigate warming over land, the warming over the ocean is related to global emissions, so we may not have much control on what happens to the extremes here. So we have to take actions to protect ourselves against extreme events anyway. Sorry, I may be running late, but the bad news is that most of them...
It's okay, you can extend your lecture by 15 minutes, Raghu. You have more time.
That's okay. I will leave the time for questions then. I'm almost finished. The bad news is that the Indian Ocean is very warm. The mean SSTs are very warm. So even small SST anomalies will make a difference in terms of creating coupled ocean atmosphere interactions and feedbacks, triggering convection and so on. So models have a very hard time producing these small variabilities on top of high mean SSTs. So here are various models showing their SSTs compared to observations in red at various SST ranges like 24 to 25, 25 to 26, and so on up to 29, 30, 30, 31. These are another set of models. And you can see that all the models have serious biases. Okay, the typical bias is that the oceans tend to be cooler than observed, and there is more rainfall over the ocean, and the land has what is called a dry bias. So we don't know whether they are doing a wrong SST feedback and creating more rainfall over the ocean and hence supplying less moisture over land, or whether some land use prescriptions, vegetation types are missing, so that the moisture demand is not enough in the models. So that's something you have to think about, whether the rainfall here is related to the instabilities and the moisture demand from here, or whether it is related to the moisture supply from here, which may be related to some other dynamics. Okay. That's a difficult question, but if you are a modeler, you can try to tease out those kinds of details. The good news is that India has invested hundreds of crores in improving short, medium, and extended range forecast and seasonal to interannual forecast. This is an example from this past season. So tomorrow, 2 days later, 3 days later, 4 days later, warnings for heavy rainfall and so on. And you can see the widespread rainfall here. And this is, of course, related to the topography of the monsoon and the Western Ghats. And these skills are now pretty good. Okay, many of these red colors are extreme heavy rainfalls and so on. So the skill of IMD models in predicting few days ahead these extreme rainfalls is very good. The seasonal skill is, I mean, IMD would say it's good, but I'm worried that the spatial distribution is not that good. So for the farmers, that could be a problem. So extended range, 2 to 4 weeks, for example, has to be very good because farmers rely on that. So maybe the focus has to be on that time scale. The other details of the ocean's role comes from looking at these kind of examples from very nice paper by Marcus Yoakum and his collaborators from NCAR, which looked at the standard biases you get in most coupled models, which is called double ITCZ. So in the Pacific, The ITCZ should look like this, heavy rain here, and the SPCZ, which should have a tilt. But most models tend to have a zonal SPCZ, which is a serious error. It affects El Nino, it affects Walker cell, monsoon, and everything. And for the longest time, we haven't known exactly what causes it. But what this paper argues is that when they include what is called near inertial wave mixing in the ocean, which is basically inertial waves are these waves that are generated by high frequency wind forcing that produces inertial waves in the ocean when there is not enough friction. So if you get away from the surface in the thermocline, you can have water parcels moving around, or you can have other ways of generating inertial waves. And when they break, they cause mixing. So they used the energy of wave mixing. They raised it from 0.34 terawatts, which is common in most models with the prescribed mixing. They made it more realistic by including a near inertial wave mixing parameterization, which doubled the energy from the inertial waves. And you can see that when they included the inertial wave mixing, the double ITCZ almost disappeared. Actually, it completely disappeared. In a coupled model, that's not always easy to say exactly what happened, but one can diagnose to see how the ocean mixing improved the sea surface temperatures and the feedbacks between the mixed layer and the atmosphere and latent heat loss and so on and so forth. And it also shows some feedbacks all the way to the Southern Ocean. And maybe some of you are aware that the ITCZ is called the energy equator because the ocean moves energy north in the so-called Atlantic meridional overturning circulation here. In fact, it moves energy from a colder hemisphere to a warmer hemisphere because it is mechanically being forced to move heat north by the wind forcing, whereas the atmosphere moves the energy south by the ITCZ being north of the equator. So it is called energy equator, and the position of the ITCZ is argued to depend on how much energy has to be moved south to compensate for the northward energy transport by the meridional overturning circulation. Of course, there are complications when the ITCZ splits like it does over the Indian Ocean, but there are also theories on how to account for zonal asymmetries of the ITCZ and so on that are good ideas. Okay, so that's kind of the ideas that I wanted to present. I hope you are convinced that the monsoon is changing in terms of the onset, the withdrawal, the length of the rainy season, the active break periods, speed of the northward propagation, and so on. Mechanistic understanding of the links between these different components is not clear. For example, is a later onset related dynamically to an earlier withdrawal and the change in active break periods, or are they all independently controlled by different dynamics? If they are related dynamically, then the prediction business will become easier. If they are completely independent, then obviously prediction will become much harder. Ocean's role is apparently important. It's a warm ocean and it is getting impacted from the Pacific and the Atlantic Ocean. We have better understanding of the impact of the El Nino and Atlantic Ocean rather than the Indian Ocean itself. And you have to remember that the monsoon happens in June, July, August, whereas IOD happens in September, October, November, and El Nino happens in December, January, February. So you have to really understand the monsoon itself as a heat source. How does it affect Indian Ocean dipole and El Nino? Atlantic zonal mode happens in June, July, August. So if it has a predictive skill, then maybe that can also help. So these understandings are very important, but a lot of good thesis problems can come out of those because every time there is something not understood means there is good research problem there as well. On land, I didn't show the results, but on land, if you look at the relation between extreme rainfalls and local heating, only about 25% of the grid boxes on land have some relation between local heating and extreme rain events. So the instabilities created on land need moisture to come from the ocean. So you can think of it as a example of a popcorn maker. If you think about a popcorn maker with a kettle, so land is like a kettle that is getting warmed, and if you put kernels which are like convective instabilities, you cannot easily predict which popcorn kernel will pop next. It will be just popping everywhere. So that is kind of the idea, that the rainfall and extreme events are not so easy to predict because when the moisture demand happens, moisture has to be supplied from oceans. So that may determine the scale of the extreme events as well as the amount of rain in the extreme events, because the scale over which you have to advect moisture probably becomes limiting. But in that sense, the warming of the ocean itself is a serious concern, because that means we can only control so many things. Processes controlling the Indian Ocean warming are not fully understood. There is still understanding coming about the role of the Pacific Ocean and the Southern Ocean. So I will stop here. I don't know if there is a way to turn on the video somehow. You can tell me if there are questions, if people have questions or...
Yeah. Raghu, there are a few questions here. The first question is, how does ocean affect short period rainfall extremes during the monsoon? This is from Raghavendra Ashrit from the National Center for Medium Range Weather Forecasts.
Hi, Raghavendra. What is the question?
How does ocean affect short period rainfall extremes during the monsoon?
Yes, I think, Raghavendra, the question there is to look carefully at the supply from the Arabian Sea and the Bay of Bengal. I think the Bay of Bengal relation may be a little bit more obvious, because the monsoon depressions, if you look at the so-called low frequency depressions, 10 to 20 day, 20 to 60 day, they seem to be decreasing, whereas the synoptic scale disturbances, let's say day 1 to 10, seem to be increasing. So Arindam Chakravarti and Akshaya's argument is that the extreme events are a combination, large scale extreme rainfall extremes are a combination of processes from the west and the east, but a lot of the smaller scales are just from the Bay of Bengal, I think. But the Bay of Bengal supply is not all local, because the southwesterly winds actually turn east and go over the Bay of Bengal and turn around, as you well know. And that direction of the southwesterly jet, fin-later jet or low-level jet, I think depends on the strength of the convection on the Bay of Bengal itself. When there is a moisture demand from the Bay of Bengal, especially like a cyclone, you can see that it completely tilts the low-level jet eastward. So Kerala gets a lot of rain during those times, whereas when the core monsoon zone is getting more rainfall, the low-level jet is going northeastward, and then northern Western Ghats get heavier rainfall. So the Ghat rainfall is related more to the Arabian Sea with the tilting of the low-level jet, and the core monsoon zone is probably influenced more from the Bay of Bengal. So that's a kind of a long answer, but I think that is something that has to be looked at.
Yeah. The other question is, can extreme Indian Ocean dipole be treated as a precursor for estimating the weather extremes over the Indian landmass? How the evolution of IOD be related for influencing extreme rainfall events? By Upal Shah.
Yeah, I didn't get the name, but as I said, the main thing to remember is that IOD is happening in SON, but you are asking about evolution. So what I try to imply with the correlation of the Indonesian rainfall and sea surface temperatures or rainfall is that the Indonesian rainfall has a strong signal in March, April, May, and June, July, August. In fact, the rainfall over Indonesia is drier in July, August, September, wetter in January, February, March. The January, February, March doesn't have huge anomalies. Our biggest anomalies happen in June, July, August. And if that rainfall anomaly has a strong correlation over the Eastern Indian Ocean, I think that is where the relation is coming from. So the Indian Ocean dipole, I think, is a response to this interaction between the ocean and Indonesian rainfall. So the relation to the monsoon and the extreme Indian Ocean dipole is probably related to the Indonesian rainfall and the monsoon, not so much the not so much the Indian Ocean dipole itself. Okay, so I would look for relation between Indian monsoon evolution and Indonesian rainfall anomalies. Because Indonesian rainfall is also part of this Indo-Pacific tripole or the West Pacific convection and so on. So every time you move, what happens during extreme Indian Ocean dipole? You basically get a trade wind structure over the Indian Ocean, okay, because you have very strong southeasterlies over the southern Indian Ocean coming all the way to the equator. That can happen when the West Pacific convection moves far east, and that's what we call extreme Indian Ocean dipole. So I think the dipole focus is probably a bit misleading. Focus should be on heat sources, which is the Indonesian rainfall, I think. That's my thinking anyway. Don't tell the Japanese because then they will kill me. Other question?
Yeah. Can we predict drought events in the coming years by future El Nino and negative IOD years? That's from a student. Voice going. Okay. Yeah. Hello?
Okay.
Yeah.
Can we predict droughts on what?
No, and negative IOD years. Yeah.
Can we predict droughts in negative IOD years? Yeah, I think negative IOD means West Indian Ocean is cooler and Eastern Indian Ocean is warmer. But again, as I said, predictability seems to come more from the Atlantic Ocean and the Pacific Ocean. So I would look for, again, the relation of the negative IOD with the Indonesian rainfall. And so why I keep saying Indonesian rainfall is that is the Walker cell, okay, which is related to the local Hadley cell. So the droughts and wet events on the Indian Ocean are related to this local Hadley cell. If it is convecting over the ocean, then it's not convecting on land and vice versa. So ocean signal in the Eastern Indian Ocean is related to northward propagating systems and the ITCZ. So there are two time scales there. So you have to look at whether the drought is related to lack of northward propagating movements and whether that is somehow related to the SSTs over the Eastern Indian Ocean or the Indonesian rainfall. Okay, so go after the heat sources.
No. Yeah. The other question is.
By the way, let me just add. Yes, maybe your question was more subtle. There are times when there are droughts over Indonesia that are related more to the southern oscillation and not to El Nino. So even if there is no El Nino, there can be a negative southern oscillation, drought over Indonesia, and that may correspond to drought over India. So you are right. So looking more carefully at negative IODs in terms of SOI may help droughts over India. Okay.
Yeah. The other question is from Mohan Tota Satyanarayana. Bjorken's feedback over the Indian Ocean, is it not upper ocean? The mixed layer depths dictate more in SST variability rather than the deep ocean circulation, unlike in the Western Pacific.
I think the question is a little bit confused. The Bjerknes feedback in the Pacific happens in the Eastern Pacific where the thermocline is shallow. So Birkness feedback, you should understand what is Birkness feedback. If the thermocline moves and it affects SSTs, okay, when upwelling happens in the East Pacific, thermocline is lifted and there is kinetic energy to mix the thermocline waters into the mix layer. So that's why surface cooling happens. Upwelling by itself doesn't cool the surface temperatures unless there is entrainment. And if there is entrainment, the SST cools, then the east-west SST gradient changes, and that changes the winds. That further changes the upwelling. That further changes the thermocline and SST, and so on. In the Indian Ocean, the thermocline is in the east is deeper. In the west, it's shallower. But during strong IOD events, there is strong upwelling along shore winds, which are related to the Rossby wave generated from the Indonesian rainfall anomalies again. But those alongshore winds can raise the thermocline and then they can interact with the mix layer. So the mix layer thermocline interaction is important, but it's not the deep ocean circulation. It's the thermocline which is still in the top 50 to 100 meters.
Okay. The other question is, over the Western Ghats, does free troposphere moisture play any role in the sensitivity of deep convection? This is also by Mohan.
Yeah, I mean, free tropospheric moisture is always important because when you have convection, you have moisture loading that is needed to create the rain. The question is more about the instabilities that trigger the convection. So is it just pure orographic rain or is there a control of the ocean? So what it turns out that if you look carefully at the rainfall, the maximum is actually on the ocean. So as the southwesterly winds are coming, they are low speed, so they can sense the obstacle, Western Ghats, so they have to climb. So they slow down. When they slow down, the ocean is affected because latent heat loss is reduced if the winds get weaker. Then the ocean controls the moist static energy, and this the instability in the moist static energy that also plays a role in the convection over the ocean. And moisture is anyway coming in the fin later jet or the low level jet. So moisture is not an issue. Moisture is available. The free troposphere is loaded from the pre-monsoon months itself. The question is the jet is not very well organized and instabilities are not there. For example, the warmest temperatures are in March, April, May. But rainfall happens in June, July, August, right? So it's the convective heating that then drives a moisture demand, whereas during the March, April, May, moisture is being loaded by the warming and the disorganized winds. So yes, free tropospheric moisture is always available and it is needed for deep convection.
Okay. I'll take a last question. This is from Srinivas G. What would be the role of convection over the maritime continent on active Indian summer monsoon rainfall?
Yeah, so that's what I tried to indicate, that the maritime continent rainfall seems to have a very strong correlation with sea surface temperatures in the eastern Indian Ocean. And the eastern Indian Ocean seems to be the hotspot for, should I go back to the PowerPoint and show the animation again?
Yeah, you can, please.
So if I go back, I don't know if I'm still sharing. Can you see this?
Yeah.
So if you look carefully here, so this is where all the action is. Not much is happening here. So you can see that the ITCZ is trying to move north with the sun. It moves north with the sun here, but not here. So you get drier climate here in June, July, August because the sun is moving north and ITCZ is moving north. But here, ITCZ is getting split. So the East Indian Ocean has some role to play either in terms of a positive feedback or somehow providing favorable conditions for northward propagating systems. So you have a seasonally persistent pattern over land, and you have propagating systems coming from here. Okay, so this rainfall over the maritime continent probably affects these northward propagating systems because it affects the subsidence over the Eastern Indian Ocean. So if somebody wants to do a thesis, that's what I would look for. Look for the relation between the subsidence over here and the ascent over here. active period over the Indian region means ascent over the Indian subcontinent and descent over the ocean. So there is a relation there, which is the local Hadley cell reacting to this Walker cell. So it's a good question, but somebody has to sit down and look at the relation between the maritime continent rain at intra-seasonal time scale and the local Hadley cell. Okay. So
Okay. Yeah.
this is G. Srinivas from Thailand or what?
No, no, no. He is a postdoc in France.
All right.
Okay. Yeah. Thank you, Raghu, for your elucidating lecture on the role of the ocean on the Indian monsoon. Sitting along with me is Dr. C.V. Naidu, our head of the department, and I request him to propose a formal vote of thanks. Dr. Naidu.
Good evening to all. I thank all the researchers and students attended for the lecture entitled Ocean's Role in the Monsoon Variability, Trends and Extremes, delivered by Professor Raghu, University of Maryland, USA. We know that Professor Raghu is a renowned researcher in the world. The way of his presentation is simply superb. I have no words to express my feeling. In the recent past, Professor Narayana Garu from Central University sent some web links of Professor Raghu's lectures for the benefit of our students and research scholars. Sir, your lectures inspired students, researchers, and a teaching staff. Today's lecture enhances the value of our web series. Sir, we are very fortunate today to hear very enlightening lecture delivered by you, sir. I should be thankful to you. Our department is contributing some promising students with MSc and MTech degrees in meteorology and oceanography and doctorates. I am looking forward for your kind help in the development of our Department of Meteorology and Oceanography, Andhra University. Thank you, sir. Thank you very much, sir. Namaste, sir.
Yeah, thank you.
Namaste,
Thank you, Dr. Raghu.
Bye.
I think it should be a long day for you. I think it must be 4 o'clock early in the morning when you woke up. Yeah.
No, I'm in India now, so that's
No
okay.
problem. Then it's okay. Fine. Then it would be fine. Yeah.
All right. Okay.
Once
Bye-bye.
visit our department also, sir.
Why don't you make a visit along with Dr. Surya to give after this pandemic is over? Yeah.
Yeah. I think we'll wait for the pandemic and then.
Yeah.
Yeah.
Please.
Okay. Bye-bye.
Right. Thank you very much. Thank you very much, Raghu.
The offices.